Good afternoon, folks. How are you today? So let's review a little bit again. We are interested in solving one transcendental equation in one unknown, and let's call this unknown x. So when we say we have an equation, we basically mean something is equal to something. And when we say we have only one unknown x, that means in both sides of the equation, we know all quantities except x. Let's see what we mean by transcendental. So a transcendental value or a function is which cannot be calculated. Transcendental is which cannot be expressed exactly. So let's look at some kind of values that are transcendental. So pi cannot be expressed exactly. E to the power 1 cannot be expressed exactly. Square root of 2, for instance. There are functions, for instance, all trig functions, sine, cosine, tangent, they are all transcendental. Square root, e to the x, they are all transcendental. Essentially, most of the equations that you come across are likely to be transcendental. Then what we do is any equation that we have, we can eventually write it in the form something is equal to 0. And this something is what we call a function of x, because the only unknown there is x. But this transformation of the equation we can do in many different ways. So for instance, suppose we have an equation x squared plus 5x is equal to sine cube of x. So in order to transform it into this form, fx is equal to 0, one way we can do it is we say x squared plus 5x and we subtract sine cube from both sides. So this becomes our function of x. Another way we can do it is we can take x squared plus 5x, divide both sides by sine cube of x. Now right hand side is 1, so we subtract 1, and this 2 is a function of x. But these two functions are different functions. Although we are starting with same equation, and if this equation has a solution, then of course this equation would have a solution, same solution, and this equation would have a solution, same solution. That solution or that x value is also called root of the function. It's also solution of the equation. So that's our terminology. Now, the function may have no real root, in which case the solution does not exist, or the function may have one or more real roots. Now, before we go on to look at the roots, let's see why we want to learn numerical methods to solve such an equation. Well, first of all, the function may have no analytical solution. So we won't have any analytical method to find that solution. Another might be, there might be analytical solution, but it may be too difficult or time consuming to find. So we may not want to spend the time. Another idea may be that we don't know the function explicitly. That means it is a black box. It is embedded in a hardware or software system, and that is most likely to be the case when you are going to be using numerical methods in design of a product or a process. So most of the time you would not have that product or process functional behavior like f of x explicitly. So that's why we want to learn numerical methods. So what does root of a function mean graphically? So let's see. So here is a function. It does not touch the x-axis at all. So it is never zero. The function never evaluates to zero. So we say function has no roots. Here is another curve. It touches the x-axis at this black dot. So it has one unique root. Here, this function touches the x-axis twice. So two distinct roots. Here we have three distinct roots. So let's consider a very simple case. Let's suppose our function was sin x. We wanted to find its root. So sin x is equal to 0. So we look at our plot. So we have sin x, we plot it. And of course, it has many, many roots that we know. So it has many, in fact, infinite number of roots. Let's change the function. If we change the function to say sin x plus 5, this entire function moves up by 5 units. So now it has no roots. So you can see that it depends on the function. We may have different situations. So let's consider a very simple example. Let's say we want to find square root of a function. So given a number a, we want to find its positive root. This is very important because consider your calculator. How does your calculator square root key work? Obviously, it does not have a database of all the square roots. That would be infinite size database. And there are no analytical techniques really. If there are, they're very difficult to program. So what we do is we use numerical methods. In fact, we are going to be using one of the numerical methods we are going to learn in this course. Anyway, so let's suppose we have a calculator, very simple calculator, whose square root key is busted. So now all you can do is addition, subtraction, multiplication, division, those kind of things. So we will square both sides. We'll get x squared is equal to a. Now we want always of the form something is equal to 0. So we'll subtract a from both sides. And therefore our function would be x squared minus a. So we want to find the positive root of this function x squared minus a. Now we know from the properties of the root that x is between 1 and a. So we can search for the root between 1 and a. In our example, we will consider, let's say, a is equal to 5. So we'll always be finding square root of 5. Very trivial problem, but once we know how to solve this problem without any restrictions, we should be able to solve any problem of this type. Well, one thing we can do, just like to visualize it, we have been plotting function. We can plot this function. So we can say plotting method. Well, it's not really a numerical method. We do need to know the range of x for plotting. So we may need to experiment with different ranges. But let's suppose once we plot it, and we find the function touches the x-axis. In fact, crosses the x-axis between a and b. So now we can focus on this range which contains a unique single root. And you can see that whatever is the sign of function a, function at a, we will have opposite sign for function at b. So that would mean function of a times function of b would be always less than 0 if it contains at least one unique root. So the first thing you're going to do in lab number 1 is you are going to learn how to implement in Excel plotting a function. So you're going to be given some kind of a range within which you are going to plot the function, and you're going to find out where it touches the x-axis. In this case, crosses the x-axis. So we have a root between 2 and 3. So you will learn how to create a Visual Basic function. Before we move on, let's kind of talk about this. I just said touching versus crossing the x-axis. So in principle, mathematically, the function does need to cross the x-axis to have a root. It can just touch the x-axis. The problem is we never want to solve in practical terms this kind of a problem. Mathematically, it is okay. But practically, we don't want to solve it because what will happen is that we can never test that something is equal to something exactly when this is not a whole number. So if it is a real number, we'll soon learn uncertainties in real numbers, how computer treats it. But this is never a good test because it might always fail. X may never become that. So if that is the case, let's say function never becomes 0 really, or whenever we evaluate the function is approximate, it never becomes 0. That means it will never touch the x-axis. And even though mathematically there is a root, practically we may never find it. So what instead we do, in this case, you can see if the function is continuous at this place, the first derivative of the function is 0 because it is a minima. So what we can do instead is solve an alternate problem and say instead what we are going to do is we are going to solve for the derivative to be 0. So you can see here the derivative is negative and then exactly at the same value it will cross and become positive. So this is what the problem we will solve. So instead of f is equal to 0, we will solve f prime is equal to 0. So think of this as a different function g. So that's the key point. So practically, we never want to test for touching the x-axis. We are going to test for crossing the x-axis. But mathematically, as far as the definition of the root is concerned, it only needs to touch, not cross the x-axis. So we have two categories of methods to find root of the function. One are called bracketing methods. Bracketing methods always bracket the root all the time at each iteration, so they are guaranteed to converge. Methods such as bisection method, linear interpolation method are bracketing method. So we are going to cover bisection method in detail here. Then there are non-bracketing methods. Since they don't bracket the root always, they may not always converge. But the great thing about them is they are much faster than bracketing methods. So we are going to discuss 3 of these methods. So let's see, first of all, when I use the word iterative method, what do I mean? In iterative methods, let's say we have an unknown x. So we begin with a guess for that unknown. Let's call it x old. Then depending on the method, we compute a refinement delta x, and then we use this refinement to improve our guess called x new, which would be x old plus delta x. Now if delta x is small enough, we will stop. So this is what is called convergence criteria. When do we stop iterating or searching for our solution? Otherwise, we keep repeating steps 2, 3, 4 till we converge. So that's the key idea of this. Begin with a guess. The method gives us way to find refinement. We improve the guess and then test for convergence. So let's see what happens in bisection method. So suppose we do have a root between a and b. So of course, function at a left is negative, function at b right is positive. So function at left times right is less than 0. So what we do is we find the midpoint. So this midpoint is going to be left plus right over 2. This is our x left, this is our x right. So what we do is we define delta x, which is basically either of these. So we define our delta x to be x right minus x left over 2. That's our half the bracket length. And now we can define that every time our new value is, which is our middle value, is x left plus this delta x. So we have a way to calculate xm in a different way. So we prefer in this two-step way because in our iterative method, we said we want to first calculate delta x and then modify the new value. Now, if the root is in left half, what we want to do is we want to move this right marker to the middle. If the root is in the right half, we want to move the left marker. So then next time we are going to deal with just half the length of the original interval. So here is a graphical example. So we have currently a root between 12 and 16. So the midpoint is going to be 14. So we see the root is in right half, 14 and 16. So now we plot it between 14 and 16. Midpoint is 15. We find therefore the root is in left half. So we are going to search for the root between 14 and 15. So we plot it again. This time midpoint is 14 and a half and our root is in the right half. So next we are going to search between 14 and a half and 15. So you can see how we can make our bracket smaller and smaller each time. So let's go back to our original problem, original example. And our original example was as follows. We said we have a function f of x, which is x squared minus 5. We want to find square root of 5. And it is equal to 0. So we are going to do it manually. And my suggestion to each of you is to follow along with me with the calculations. Okay, so we have first iteration. We know the root is between 1 and 5. So we calculate what is the function at 1. So 1 square minus 5 gives us -4. What is the function at 5? Square minus 5 gives us +20. Our delta x is 5 minus 1 over 2. So our x middle would be x left plus delta x. So we will get 3. And we calculate what is the function in the middle. 3 square minus 5 is 4. So second iteration, so we have left positive sign, left negative sign, middle positive sign, right positive sign. So we have minus, plus, plus. So therefore, our root is going to be in the left half. So we won't move the left marker, but move the right marker to 3. So this 5 would change to 3. The function is still -4. This is +4. Our delta x now is going to be 1. Notice every time it halves. And our middle point would be 1 plus 1 is 2. We calculate 2 squared minus 5 is -1. And then we go third iteration. This time, notice our function values are minus, minus, plus. When it is minus, minus, plus, now our root is in the right half. So we move the left marker to 2, leave the right marker at 3. So our left value is now -1, right value remains plus. Our delta x now is half of what it was. The x middle is left plus delta x 2.5, and we keep on going. Calculate 2.5 square minus 5 is 1.25. So you can see first of all that delta x reduces by factor of half, and we get closer and closer to the root. So you can see that if we continued for 5 iterations, after 5 iterations, we would say our root is 2.125 plus minus 0.125. So let's talk about this delta x, which is our uncertainty, plus minus 125. We don't care usually about the sign. So whenever we are talking about uncertainties, it is understood it is plus and minus. We only talk about the magnitude. So we see that this magnitude is less than 0.5 times 10 to the power, whatever is the largest number that we can put here would be great. So we can see that the only largest number we can fit here is 0. So our approximation has 0 correct decimal digits. So this answer, x is equal to 2.125, has 0 correct decimal digits. So algebraically, what we are saying, in our table, we calculated delta x. Then we calculated x middle, which was x left plus delta x. If the root is in right half, we want to change x left. If the root is in left half, then we want to change x right. And this is what we are going to code in our spreadsheet for the lab number 1 next Monday. So we just talked about convergence criteria. It turns out there are 3 convergence criteria we could possibly use. Now we are assuming a rounding machine, and again we are going to talk about this rounding versus truncating later on. But let's just look at convergence criteria. So one we call is an absolute bound. What the absolute bound does, error bound does, is it helps us determine exact number of correct decimal digits, CDD for short. So if we find that our absolute uncertainty is less than some epsilon absolute, and how do we choose this? We specified it based on how many CDD we desire. So if we desire, say, 10 CDDs, we will choose 0.5 times 10 to the minus 10. We can also use a relative error bound. We can use relative error bound only if x is a non-zero value. So relative error would be delta x over x. Of course, we are always looking at magnitude. Typical books. So the reason I'm using these epsilon symbols is most of the books would just say this is specified or you choose, but they don't know how you should choose. So what I'm teaching you in this course is that absolute criteria is related to correct decimal digits, and relative criteria is related to significant digits. What it does is not determine exact number, but minimum number of significant digits. That means you could have potentially one more significant digit in your actual answer. So it kind of gives you a minimum conservative guarantee. A third one is that the function at x nu, which we want ideally to be 0, is less than some small quantity epsilon f. Now this depends on the function itself. So that means this is problem dependent. Again, this is a criteria often many textbooks use without telling you how to specify epsilon f. We are going to ignore this third criteria altogether because this would become problem dependent. These are easier to decide or desire. We can say we desire 5 correct decimal digits, or we desire 7 significant digits in our answer. So this is what you are going to do in Monday's lab. You are going to set up bisection method. You're going to set up a table. You're going to put in your inputs. So in my case, for instance, I have a function x squared minus 5. This is what we have been dealing with in the class. I'm going to set up another function to calculate delta x using bisection method, which we know is x right minus x left over 2. So you're going to learn to program this spreadsheet in this way. We are going to do iterations, and you can see for this problem, our square root problem, using bisection method with initial guesses 1 and 5, and let's say we are shooting for 4 correct decimal digits. It took us 17 iterations to get there. So this particular result that we have, 2.23605, is good to 4 correct decimal digits. So if you look at square root of 5, square root of 5 is 2.236068 rounded. we got our approximation, we got was 2.23605. So you can see we match exactly 1, 2, 3, 4 correct decimal digits. And for our this problem, square root problem, it took us 17 iterations. So let's see the convergence behavior of the bisection method. So if the initial bracket AB contains a unique root, and we know all bracketing methods are guaranteed to converge to the unique root, bisection method converges linearly, and it's the slowest of the method. So how do we decide about this? It turns out that if we say our next delta is basically some constant times the previous delta that we had to some power m. So in this case, we know that our next delta was half of the previous delta to the power m. M was 1. So since m is 1, we say linear rate of convergence. If m was 2, we will say quadratic rate of convergence or parabolic rate of convergence, and so on and so forth. So this m power, ideally we want as high as possible. That way we can reduce delta x by a huge amount every iteration. So in fact, you can see after one iteration, delta x would be b minus a over 2. After 2 iterations, it'll be half of that. That means instead of 2 to the power 1, it'll become 2 to the power square. So after n iteration, delta x will become b minus a 2 to the power n. And the reason we are going to stop is that we would satisfy our criteria that this is less than epsilon absolute. So now we are going to integrate. How do we choose epsilon absolute? We'll choose epsilon absolute to be 0.5. We choose 0.5 because we are going to assume we have a rounding machine. We are going to talk about that later on. Times 10 to the minus CDD. This is the number we desire. So that's our criteria. So now we can rearrange this. So let's bring b minus a over 0.5 times 10 to the minus CDD to one side, less than equal to 2 to the power n. So now what we can do is we can take natural log of both sides. So when we take natural log of both sides, we will get here n log 2. So what we can do is we can divide both sides by n log 2. So we rearrange, we'll get n is greater than or equal to log of b minus a divided by 0.5 times 10 to the minus CDD divided by log of 2. So that's our formula. So let's use it for our example. So for our example, function was x squared minus 5. Our initial guesses were that root is between 1 and 5. So A is 1, B is 5. We wanted 4 correct decimal digits. So we substitute all this in our formula up here. So let's do 5 minus 1 divided by 0.5, 10 to the minus 4. Take log of it, divided by log of 2. We will get 16.3. So obviously 16 is too few an iterations. So we need at least 17 iterations. And you may remember we just did our spreadsheet and we found it took 17 iterations exactly to converge.